You know, I was standing in the supplement aisle at the grocery store this morning, staring at this bottle of resveratrol that cost more than my weekly coffee budget.
Ah, the longevity aisle.
Yeah, and I just had this, I don't know, this moment of existential doubt. I'm buying the kale, I'm doing the intermittent fasting, I'm taking these cold showers that make me absolutely miserable. I'm doing all the right things.
It's the modern condition, right? We're all trying to biohack our way to immortality, one expensive pill at a time.
Exactly. But then I think about my great uncle. Smoked a pipe, ate red meat 3 times a day, never exercised, and lived to be 96.
Wow.
Sharp as a tack till the very end. So it just makes you wonder, is this all just a lottery? Is my expiration date just stamped on my DNA? And all this green juice is just theater?
That is the ultimate question. Nature versus nurture. Is it the genes or is it the lifestyle?
Right.
And for a long, long time, the scientific consensus was actually pretty optimistic for people like you who, put in the work.
Okay, I like optimistic. What was the standard line?
The standard line was that only about 15 to 25% of your lifespan is heritable. The rest, the other 75, 85%.
That's on me.
That's on you. That's your environment, your luck, your kale and your cold showers.
See, I like that math. It means I'm in the driver's seat.
Well, I would say don't get too comfortable in that driver's seat.
Oh,
because I've brought a stack of research today that is going to seriously shake that assumption. We have a brand new paper just out last month, January 2026, by Shenhar and his team. And it suggests we have vastly underestimated the power of our genes.
Vastly underestimated. That doesn't sound good for my sense of control.
It's a bit of a game changer.
Well,
But before you go and return that resveratrol, we also need to talk about the software of those genes' epigenetic.
okay.
And then this fascinating 1-2 punch study on fruit flies that suggests that even if the genetic deck is stacked, we might be learning how to reshuffle the cards completely.
Okay, so the mission today is to figure out, are we doomed by our DNA, or can we actually hack the system?
That is exactly the mission. We're going to break it down. First, this new data on heritability, the hardware we're born with.
Right, hardware.
Second, we'll look at the software, how things like diet and even our ancestors' trauma can program that hardware. And third, the hack, this study that combines 2 different approaches to actually, break the biological ceiling.
Let's start with the hardware then. You said the old rule of thumb was 15 to 25%. If it's wrong, why was everyone so sure about that for so long?
It all comes down to how we analyze death. See, historically, researchers would look at these huge family trees, twin registries, going back 100 years or more.
Seems logical. If longevity runs in the family, the numbers should show it.
Theoretically, yes. But there was a massive flaw, a huge noise factor that distorted everything. We weren't separating extrinsic mortality from intrinsic mortality.
Okay, those sound like terms we need to unpack. Extrinsic is external.
Exactly. Think about the year 1850. Or even 1920, if you look at the death records, what are people dying of?
Cholera, tuberculosis, wars, childbirth, getting kicked by a horse.
Exactly. Those are all extrinsic factors. They are violent, random, infectious events imposed from the outside. Now, imagine you have the genetic potential, the perfect DNA to live to be 110.
Okay.
But you drink contaminated water at age 25 and die of cholera.
The data just says I had a short lifespan.
Right. But it wasn't because your body failed. It was because the world killed you. That is extrinsic mortality, and it creates so much statistical noise that it just masks the genetic signal.
So it makes longevity look random, because getting hit by a bus is random.
Precisely. That is the argument Shenhar and his team are making. They realize that if you really want to know how much genetics matter to aging, you have to mathematically strip away the bus accidents and the plagues. You have to isolate what they call intrinsic mortality.
Which is just the pure biological decline, the engine wearing out.
Correct. So they use some very sophisticated mathematical modeling on these huge Danish and Swedish twin registries, and also the siblings of American centenarians. They filtered out all that extrinsic noise.
And when they cleaned up the data, what happened to that 15% number?
It skyrocketed. When you look purely at intrinsic aging, the heritability of human lifespan jumps to around 55%.
Whoa. 55, that is a massive jump. You're saying more than half of the equation is written before I'm even born.
It's looking that way. And the most compelling proof came from the twins. So, just as a quick refresher, monozygotic identical twins share 100% of their DNA.
Right.
And dizygotic fraternal twins share about 50%, like any other siblings.
So if genetics are that big a deal, identical twins should die at almost the exact same time.
In the old, noisy data, they didn't. One might die in a war, the other of old age. But once Schenhar stripped away those extrinsic deaths, the survival curves for identical twins became incredibly tight. They tracked each other almost perfectly.
That's eerie. It implies there's a biological clock ticking away that's set to a pretty specific time.
It implies a biological expiration date, or at least a very steep drop-off curve that is hard-coded. So about half of your potential longevity is just hardware.
Okay, I have to be honest, that feels a little defeatist. It sounds like you're saying I can eat all the kale I want, but if my hardware is rated for 78 years, that's it.
While 55% isn't 100%, there's still almost half the game left to play.
True.
But it does shift the perspective. It means we can't just lifestyle our way out of a bad genetic hand.
But a computer isn't just hardware, right? It needs an operating system to actually do anything.
And that brings us perfectly to the software. This is epigenetics. This is where that other 45% and maybe the real complexity of the whole system lives.
I feel like epigenetics is a buzzword that gets thrown around a lot. But what is it? Physically? Is it a thing you can point to?
Oh, it is very real. The best analogy I've heard is a musical score. Imagine your DNA, that 55% hardware, is a sheet of music. Beethoven's Fifth Symphony. The notes are written in ink. You can't change them.
A C sharp is a C sharp. You can't rewrite the composer.
Right. But you could give that same sheet music to two different conductors. One plays it fast and aggressive. The other plays it slow, melancholic. Maybe they emphasize the brass section.
The interpretation changes everything.
The interpretation is everything. That is epigenetics. Physically, these are chemical marks, mostly methylation groups, that attach to your DNA. They don't change the code itself, but they tell the cell, read this gene loudly or ignore this gene completely.
So the DNA is the library, but epigenetics is the librarian deciding which books get taken off the shelf.
That's a great way to put it, and the power of this librarian is just shocking. The classic example in nature, and I think it's the most mind-blowing one, is the honeybee.
The bees, yeah, you mentioned this. This is the queen versus the worker bee thing.
Yes. A queen bee is huge. She's fertile. She lives for years. A worker bee is tiny, sterile, and lives for just a few weeks. They look and act like completely different species.
But they're not.
They are clones. They have the exact same DNA, 100% identical hardware.
So how does one become a queen and the other a worker?
It's purely the software. It's their diet. When a larva is chosen to be a queen, it gets fed royal jelly.
The fancy stuff you see in skin creams.
The very same.
Yeah.
But for a bee, it's not just nutrition. Royal jelly has this compound that stops DNA methylation on certain genes. It literally flips a switch that says, unlock the queen software.
So the potential to be a queen was hiding in the worker bee's DNA the whole time.
The whole time. It was just silence. The environment, in this case the food, reached into the nucleus and reprogrammed the destiny of that organism.
Okay, but that's bees. Does this happen to us? I'm assuming if I eat a jar of royal jelly, I don't turn into a giant fertile monarch.
Not quite, no. But the principle holds. This is why identical twins, who start with the same DNA and the same epigenetic marks at birth, can look so different at age 60. One smoked, one didn't. Their software diverged.
But here's where it gets a little darker. It's not just my lifestyle writing my software, is it?
No. And this is the part that usually stops people in their tracks. We are talking about transgenerational epigenetics.
The sins of the father.
Or the hunger of the mother. The most famous case study is the Dutch hunger winter. In 1944, the Nazis blockaded the Netherlands. It was brutal. Food rations dropped to something like 500 calories a day. People were starving.
And obviously that's just horrific for a pregnant woman.
Horrific. But researchers tracked the babies born during or just after that famine, and they found that these famine babies had significantly higher rates of obesity, diabetes, and schizophrenia compared to their own siblings born just a few years earlier or later.
But why? If the war ended and they grew up with plenty of food, why wouldn't they just bounce back?
Because the fetus learned something in the womb. The mother's body sent chemical signals to the developing child saying, "The world is starving. Calories are scarce. You need to build a metabolism that hoards every single bit of energy."
So its software was set to extreme survival mode.
Exactly. But then they were born into a world of abundance. Their hardware was running software designed for a famine, in a world of plenty, and that mismatch caused the disease.
Wow. And it goes even deeper than that, doesn't it?
It does. There are studies in mice and rats, Michael Skinner's work is famous for this, where they exposed pregnant rats to pesticides. They found health defects in the pups, which you'd expect.
Sure.
But then they looked at the grandpups and the great-grandpups.
4 generations down the line.
4 generations. The defects persisted, the chemical marks on the DNA were passed down, or Isabel Mansuzi's work on trauma. She separated mouse pups from their mothers, creating severe stress. Their great-grand offspring showed depressive behaviors and risk-taking, even though they had happy, safe childhoods.
That is, honestly, it's terrifying.
Hmm.
It implies my great-grandfather's bad decade is essentially haunting my cells right now.
It suggests that the software has a memory. It's not wiped clean. We carry the scars and the adaptations of our ancestors.
Okay, so let's take stock. We have the hardware, that 55% from Shanhar. We have the software programmed by my life and my ancestors' lives, which seems almost impossible to control. It feels like we are stuck.
It does feel very deterministic, but this is the pivot point. This is where science stops just observing the problem and starts trying to fix it.
Enter the fruit flies.
Enter the fruit flies.
Yeah.
This is the core study. It's a deep dive favorite because it doesn't just look at one theory of aging. It combines 2 massive competing ideas to see if they can work together.
Because aging isn't just one thing breaking, it's a mess.
It's a total mess. So they decided to target 2 different mechanisms at the same time, a 1-2 punch.
Okay, let's look at punch number 1, cellular reprogramming. This is the sci-fi part.
This is the Nobel Prize-winning part. Shinya Yamanaka discovered 4 specific proteins, they're called transcription factors, that can take an adult cell, like a skin cell, and turn it back into a stem cell.
The factory reset. It makes the cell young again.
Yes. They're called the Yamanaka factors, often just OKSM. You expose cells to these, they lose their old age marks, they become pluripotent, they can become anything.
So why aren't we all injecting this stuff and living forever?
Because of the teratomas.
Right, the tumors with teeth and hair.
Nasty stuff. If you just blast an animal with these factors continuously, the cells don't just become young, they become confused, they forget who they are completely and just start growing wildly into these monstrous tumors.
Okay, hard pass on the tooth tumor.
Wisely. But researchers found a workaround, pulsed reprogramming. Instead of turning the switch on forever, you flick it on for a few hours, then off for a few days. You give the cells a little youthful reminder without wiping their memory.
So you nudge them toward youth without letting them go full toddler.
Exactly. So that's intervention 1. Now punch number 2.
The zombie cell hunter. Senolytics.
Right. This targets senescent cells. As we age, some of our cells get damaged. Usually a damaged cell does the honorable thing and commits suicide. It's called apoptosis.
Takes one for the team.
But sometimes that mechanism jams. The cell doesn't die. It just sits there. It becomes a zombie. And it's not quiet. It pumps out this toxic inflammatory soup called SASP.
It's like a rotten apple in the barrel. It makes all the healthy cells around it sick.
It causes chronic inflammation, degrades tissue. So senolytics are drugs designed to finally kill those zombies.
So we have 2 strategies. Reboot the good cells and take out the trash. What happened when they tried these on the fruit flies separately?
And this is where the nuance really matters. When they used senolytics alone, just killing the zombies, the flies stayed healthy longer, they had a compressed morbidity, they were spry old flies, but it didn't increase their maximum lifespan, they still hit a wall. And weirdly, the study found that once they started dying, they died faster.
That seems backward. You cleaned up the toxic cells. Why would they crash so hard?
Think of it like a house. The zombie cells are piles of toxic garbage. Senolytics is the cleaning crew. They remove the garbage. Great. The house is cleaner.
Yeah.
But if the floorboards are rotten and the roof is leaking, that's your lack of functional stem cells. Removing the garbage doesn't fix the house. You've just revealed the holes where the garbage used to be.
And you have no one to fix the holes. Your repair crew is exhausted.
Exactly. You fired the bad employees, but you haven't hired any new ones.
Okay, so that's why senolytics alone didn't work for max lifespan.
Oh.
What about the reprogramming alone?
It did the opposite. It protected the maximum lifespan, it pushed the ceiling up, but it didn't do as much for their average health.
So naturally they combined them.
The synergy, this is the aha moment. They pulsed the reprogramming to rejuvenate the stem cells, hiring a fresh repair crew, and they used senolytics to clear out the toxic waste first.
And the result?
It broke the ceiling. They saw a significant extension in both mean and maximum lifespan. The flies lived longer and they stayed healthier for longer.
Because you have to fix the environment and the repair capacity.
Precisely. The study showed they're necessary for each other. Trying to rejuvenate a cell that's swimming in toxic zombie juice doesn't work well. Cleaning up the juice but having no young cells to rebuild, you also fail. You need the cocktail.
This feels like we're starting to see a grand unified theory of longevity emerge. It's not one magic bullet.
It's not. It's going to be a protocol, a maintenance schedule.
Scrub the damage on Tuesdays, reboot the system on Fridays.
Something like that. It redefines aging not as this single slide into oblivion, but as a solvable engineering problem with multiple failure points.
Which brings us all the way back to where we started, that 55% heritability number from the Shenhar paper. The hardware.
Hardware, yeah.
If Shenhar is right, and I have a genetic expiration date hard-coded into me, does this fly study make that irrelevant?
That is the trillion-dollar question. If Shenhar is right, our natural limit is pretty hard-coded, but the Cower study suggests we can edit the code as it's running.
If I can reach into the cell and turn on the Yamanaka factors, I'm essentially overriding the instructions I inherited.
You're rewriting the sheet music. You aren't just interpreting it differently. You're changing the notes themselves.
So if we look 50 years into the future, say we perfect this cocktail approach.
If this translates to humans, and that is a massive if, we could be moving into an era where heritability becomes a historical footnote. If you can clinically reset the age of your cells and clear out the damage, the fact that your grandfather died at 60 might not matter at all.
We go from being passengers to being the mechanics.
Or even the designers. It changes the definition of what it means to be human. We've always defined ourselves by our mortality, our limits. What happens when those limits become negotiable?
That is the thought that's going to keep me up at night. Probably longer than the kale debate.
It should. We are standing on the edge of a very different world. The hardware might be 55% of the story today, but tomorrow, it might just be the starting line.
Well, until we get the reboot and scrub cocktail at the pharmacy, I guess I'll keep eating the blueberries and trying not to get hit by a bus.
Can't hurt the software. And avoiding the bus is always solid medical advice.
Thanks for taking us through the code of life today. It's equal parts terrifying and hopeful.
My pleasure.
And to you listening, whether you're running on good genes, bad genes, or just a lot of coffee, keep asking the hard questions. We'll see you in the next deep dive.